We will now discuss a very important property of the Lebesgue measure, namely translation invariance. Okay, so we will start with the important lemma. So lemma, let omega and omega prime be open sets in Rn. T omega to omega prime homeomorphism. So these are homeomorphic open sets. Okay, and E contained in omega is Borel. That means it belongs to Borel sigma algebra if and only if TE is Borel. So Borel sets get mapped to Borel sets and nothing else can get mapped to Borel sets. Okay, so proof. So we set S equals set of all E contained in omega such that TE is a Borel set. So clearly omega and phi belong to S because T of omega is omega dash, which is open, therefore it's Borel. Empty set is Borel and therefore there is no problem. Now if T of E complement, because T is a bijection, this is nothing but T complement, and also T of union EI is equal to union I equals 1 to infinity T of EI. And therefore, from these two facts, it follows that S is a sigma algebra. Because this shows that it is closed under countable unions and this shows that it is closed under complementation, and therefore S is a sigma algebra. And now open sets get mapped to open sets because T is a homeomorphism, and therefore S contains all open sets implies S contains all Borel sets. So given any Borel set, T is a Borel set. Now converse, apply this argument to T inverse. So then automatically the converse gets true. Okay, so that proves this lemma. And so now as a special case, let us take omega equals omega dash equal to Rn and x naught in omega Rn fixed, and we take T of x as the mapping x plus x naught. So it's just translation by x naught and therefore that is a homeomorphism. So E Borel by lemma if and only if TE Borel. Okay, so now let E be Lebesgue measurable and let A be contained in Rn. Okay, we want to show that T is also Lebesgue measurable. Now before that, you take, if I is a half open box, then I plus x naught is also a half open box, and both have same measure. Because the volume of the box does not change by translation. Okay, so from the definition, how is the definition of mu star? Mu star is infimum of all sigma mu EI, where EI is a box. Okay, so therefore by definition mu star of any set E is the same as mu star of T for all E contained in Rn. Now if you take any E is a Lebesgue measurable set and A contained in Rn, then you have, let us compute mu star of A intersection T plus mu star of A intersection TE complement. This is the kind of computation you have to do to study mu star measurability. So this is equal to mu star of T inverse A intersection E plus mu star of T inverse A intersection E complement. That's equal to, now mu star of T of anything is the same as the original mu star, so T inverse of A intersection E plus mu star of T inverse of A intersection E complement. But this is nothing but E is Lebesgue measurable, therefore this is mu star of T inverse of A and T or T inverse are both homeomorphisms, and we just saw they are just translations, and therefore the same as mu star of A. So this implies that TE is Lebesgue measurable. Similarly, apply to T inverse. Okay, so then we have proved the following theorem. X naught in Rn fixed, Tx equals x plus x naught, then E contained in Rn is Lebesgue measurable if and only if Te is Lebesgue measurable, and in this case Mn of E is the same as Mn of T of E. So this property is called translation invariance. Of the Lebesgue measure. So a measure, Borel measure is said to be translation invariant if the measure does not change under the translation mapping. Okay. So definition: mu, a Borel measure on Rn, we say that mu is translation invariant if for every Borel set E we have mu of T equals mu of E, T equals T of x equals x plus x naught. Okay, so now the Lebesgue measure is translation invariant. What are the other properties we have seen? Important properties. Lebesgue measure is finite on compact sets. Lebesgue measure is outer regular, namely it is determined entirely, it's the infimum of mu star of U open set containing any set E. Okay, so now it happens that these properties completely characterize Lebesgue measure. Any other measure which has the same properties will just be a constant multiple of the Lebesgue measure. If you take a measure, multiply it by a positive constant, you get a new measure. Okay, but essentially the measurable sets are the same, and therefore this. So we have the following important theorem. Okay, let nu be a Borel measure on Rn such that 1. Nu of k is finite for every k contained in Rn compact. 2. Regularity. So nu of E equals infimum of nu of V, V contained in E, V open. 3. Nu is translation invariant. Then there exists a constant C greater than 0 such that nu E equals C times Mn of E for every E Borel. So proof, you take Q to be 0 1 cross 0 1 cross 0 1 n times. So what is Mn of Q? It's a unit cube and therefore that's equal to 1. So now let n be greater or equal to 2. Now we take this cube and subdivided it by drawing lines parallel to the coordinate axis into cubes of size 2 power minus n. So n bigger than 2, then we can write Q can be written as the disjoint union of 2 power n small n boxes in the collection Gn described earlier. So what was this Gn? It was the set of all cubes of size 1 by 2 power n and whose vertices were at the integral lattice points with this mesh of 1 by 2 power n. And therefore you can take the unit cube and simply subdivide it into each direction into 2 power n parts, and therefore you have 2 power n times n cubes. Each of them is of the same size and they are all this thing. So let nu of Q equal to C, which is strictly positive. Then nu is translation invariant, implies all subcubes above have same measure. So let us take Q tilde one such subcube. Then what do you know? That we know that 2 power nn nu of Q tilde, this is nothing but nu of Q, because Q is the disjoint union of 2 power nn boxes. Okay, so let's say box, subcube, subbox, let's say. Okay, so you have this is equal to that, and that we saw is C, which is C times 1, and therefore I can write the C times Mn of Q, which again by translation invariant is C times 2 power Nn of Mn of Q tilde. Okay, so this implies that nu to the Q tilde equals C times Mn of Q tilde for all Q tilde in GFN. But then we proved this lemma that every open set is a countable disjoint union of elements from the union Gn. Okay, and therefore if U open, U is the countable disjoint union of half open boxes from union Gn over n, and that implies that you also have that nu of u equal to C times Mn of u. Then condition 2 implies, because it's nothing but the infimum of all open sets gives you the measure of this thing here, and therefore this condition 2 implies that nu of E equals C times Mn of E for every E Borel. Okay, so this proves the theorem. So finiteness on compact sets, translation invariance, and outer regularity, so these determine completely the Lebesgue measure. So let us apply this to a very nice result. So theorem: A Rn to Rn, a linear transformation. Then E Lebesgue implies AE is Lebesgue. Lebesgue means Lebesgue measurable. So E Borel it's also true for Lebesgue measurable. Okay, we will. AE is Borel, and Mn of A of E is nothing but modulus of the determinant of A times Mn of E. So this is the meaning. So if you have a linear transformation, you have a matrix, so you have a determinant, and the meaning of the determinant is that if you apply the linear transformation, then given any Borel set, the measure gets multiplied by the modulus of the determinant. So this is the geometric meaning of the determinant of a matrix. Okay, so step 1. Let us assume A singular. Then A of Rn is contained in a proper subspace of Rn. Let me not write here AE Borel. Then E Borel implies, okay, this. Okay, so now if E is any Borel set, okay, in Rn, then what is A of E? A of E is contained in a proper subspace, implies AE is Lebesgue measurable by the completeness, and mu of Mn of AE is 0. Because it is in a proper subspace, we know that the measure of a proper subspace R1 in R2, etc., we did this calculation, always in a proper subspace the measure is 0. Therefore, implies star. Because Mn of AE is 0. So in this case, Borel may be a Lebesgue measurable set. I am not saying it is a Borel measurable set. Okay, that's why I erased that portion. Step 2. So now we assume that A is singular. A is non-singular. So then it becomes a homeomorphism. Therefore, E Borel implies if and only if AE Borel. So E Borel by lemma if and only if AE is Borel. And you define nu of E is Mn of AE. Then nu is a Borel measure. If K is compact, continuous image of compact set is compact. So AK is compact, and therefore implies Mn of AK equals nu of K is finite. Then if E is contained in V open, then AE is contained in AV, and AV is also open, and vice versa. Therefore, you have, let us compute infimum of nu of V, V contained in E, V open. This is equal to infimum of Mn of AE, AV, sorry, V contained in E, V open, by definition. And that because of AE contained in AV is the same as V contained in E, and therefore this can be written as infimum of Mn of AV Mn of U, U containing AE, U open. And that by definition of, by the properties of Lebesgue measure, this is Mn of AE, okay, which is nu of E. Therefore, condition 2 is also satisfied. Nu of E is the infimum of nu of E. Finally, translation invariance. So, x naught in Rn, and let us take nu of E plus x naught. This is Mn of AE plus AX naught, but this is equal to Mn of AE, which is nu of E. Therefore, nu is also translation invariant. Therefore, this implies by theorem there exists a CA greater than 0 such that Mn of AE, which is nothing but nu of E, equals C times Mn of E, CA times for every E Borel. Step 3. So, if A and B non-singular, clearly C of AB equals C of BA equals CA times CB, because the measure of AB of E is nothing but the CB times CA times measure of BE, which is CA into CB times measure of E, and therefore C of AB is same as CA times CB. Okay, step 4. Let us take A orthogonal. So, if A is orthogonal and if you take E equals unit ball, this implies AE is the same as E, because, and therefore CA equals 1, which is modulus of determinant A. Step 5. Let us take A equals A given by the diagonal matrix lambda 1 lambda n. Diagonal lambda 1 lambda n, lambda I are all greater than 0, 1 does into I less than n. Okay. Then you take E equals standard closed standard unit cube. Let us say E equals pi, I equals 1 to n, 0, 1. So then what is A of E? This is pi, this is a diagonal matrix, so I equals 1 to n, 0 lambda I. That means Mn of AE equals product I equals 1 to n lambda I, which is equal to product I equals 1 to n lambda I times mn of u for the cube. So this is a constant for this particular set, so it has to be for every other set, and therefore this implies that CA is equal to product I equals 1 to n lambda I, which is nothing but the determinant of A. Step 6. So A, any non-singular matrix we have the polar decomposition. A can be written as R times Q, R positive definite, Q orthogonal. This is the same as any complex number can be written as mod Z into e power I theta, okay, R e power I theta mod Z into e power I. Similarly, you take A and you find R such that R square equal to A transpose A or A transpose. Okay, and then R, the square root of this, so this matrix R you can find is just like this, because this is a positive definite matrix, and therefore you have, and you take Q is equal to R inverse A. Okay, so this is called the polar decomposition. It's the same as writing a complex number in terms of its modulus and its argument. Okay, so R itself is positive definite, therefore you can write this as P D P inverse, P or rather P transpose, P orthogonal, and then D equals diagonal, and determinant of D in all this is nothing but modulus of determinant of A. Determinant of D is the determinant of R, and that is nothing but the modulus of determinant of A. And now you have C of A is equal to CP, CD, CP transpose, CQ. All these are 1, and this is equal to mod determinant of A. Okay, and that proves this theorem. So the determinant, this is the geometric meaning of the determinant, and we have using this fact that the Lebesgue measure being translation invariant, regular, and finite on compact sets determines the measure itself.